Howdy, and welcome back to our EET 260 microcontroller applications. In week 3, lecture 1, we demonstrated some discharge down to some particular voltage. 1.4 volts was what we determined to be in I think maybe the last experiment of week 1 and 2. We determined 1.4 volts to be the approximate threshold voltage at which a basic stamp input, if it's going high, changes from a 0 to a 1, or if it's going low, changes from a 1 to a 0. So we're back at it again with some, let me adjust this a little bit. We're back at it again with another RC charge-discharge circuit, and this time we're going to use a program from our basic stamp collection. It's posted in Blackboard, of course, and that program will be a just slightly modified version of polledrctimer.bs2, which I believe is from page 147 of What's a Microcontroller. And we are going to compare our result to our spreadsheet result for discharging our capacitor through a resistor. Now, if we look at this circuit here, you can see there's an I/O pin that will charge this capacitor through a 250 ohm resistor. That's only there to limit the current so that we don't damage the high side driver from the I/O port. That's the side of the I/O port that connects us with a plus power supply. And so that will charge this thing up. I have I think you can see down here, there's a trim pot right there, if you can see me pointing right there, that blue thing. That's a trim pot, and right now it's set to its max, and it's 10,000 ohms. Maybe I could move these up a little bit here. You can see I have 2 of my 1,000 farad capacitors in there to give us 1,000 microfarad capacitors. Like each one is 1 millifarad. So when we put them in parallel, you have to charge both of them to get any voltage to reflect stored charge. So putting capacitors in parallel adds them. And we have 2,000 microfarads. And once we turn this I/O pin to an input, it becomes very high resistance, and almost no current goes back toward the I/O pin. It will all discharge through the 10K resistor. Alright, so given that, I think we should go run this program. Well, let's look at our spreadsheet first. Our spreadsheet says I started us out at 4.4 volts. Maybe I should you can download a copy of this and run it as you like. I'm looking at our charged up capacitor right now, and this would be 5 volts here, so it's looking closer to 4.5 volts to me. And not that a tenth of a volt is going to matter that much, but let's just try to get as good as we can, and we'll move our column over here. And if we look here, it looks like we will go at about maybe that's 23 out of 25 seconds. Here's 20 right here. Here's 25, so that's 23, maybe a whisker over. 23 and a quarter, something like that, I don't know. Let's try it in real life and see what our what our computer says that it is, we're going to run a program. And let me come over here. So we're in the basic stamp editor, and we're going to run a program where we, again, this is a modified version of polledrctimer.bs from page 147 of What's a Microcontroller, where I've changed it. I haven't changed any of the top part here. We'll spend 5 seconds charging up the capacitor, although it looks like it's already there. And then we turn pin 7 to an input. So we drove out on pin 7 to charge it up. We made this pin 7 high, and then we sent out some messages, capacitor charging, measure decay time now. Well, actually, you don't measure it quite yet. You count down to 5, 4, 3, 2, 1, 0. Then we change to the input here, so the pin 7 becomes a very high input resistance. And what we do is we wait half a second, we increment our time counter, and we look for the input value of pin 7, and then we print out what the time counter is, some carriage returns, and return back up to the top of the debug terminal, and we just keep looping. And so we do loop until input 7 goes low, that is until it goes below 1.4 volts, and then we print out, you know, how many what the time was. And I've changed it from tenths of a second, which it was. This used to be pause 100, which is 100 milliseconds or a tenth of a second. I've now made it say pause 500, which is 500 milliseconds or a half of a second, and at the end it prints out the number of halves of a second. So we can run this thing here, and it will actually, now it's saying 5, 4, 3, 2, 1, 0, and it's counting up over here. And I don't know if I can zoom in on this. There's probably a way to change the font of this terminal to be larger, but I'm up to 35, 36. I keep going, 40. So it quit at 46, which would be, in halves of a second, that would be 23 seconds. And so that's a pretty good match between our actual behavior here and our, as you can see, it's discharged down below. Our actual behavior and what we computed would happen here. We said, I don't know, a little over, maybe 23 and a half or something. But anyway, we got 23 seconds, and that ain't bad. So there's a place now, you know, if we were measuring something there, if we knew the values, some tester, we had tested these capacitors together and knew that value, we could determine the value of this resistance here, or vice versa. If we knew this resistance to some accuracy, we could figure out the value of those capacitors by watching this decay curve. So once again, we achieve a kind of an analog to digital conversion by measuring time. And I think I said this before, but I'll say it again. And you know, this will probably be in the homework or in some kind of quiz we do. There's this idea of a single slope or a dual slope integrating analog to digital converter. If you were to charge a capacitor with a constant current source, that is, maybe you used a transistor circuit and you know, had some feedback so that the current was constant charging that capacitor, then what you would find is that the voltage on that capacitor would not increase or decrease in this exponential wave shape, but it would be linear. And being linear, it's pretty easy to, once you've measured time, to convert that to a voltage. So let's say we had some sort of circuit where we wanted to measure a voltage, and so we sampled that voltage somehow and charged up a capacitor with that voltage. Then we let that capacitor discharge through a constant current source and measured when it crossed, say, 1.4 volts in this case. We had some kind of threshold detector. Then if we know the time between letting go of the initial charging circuit and when we crossed 1.4 volts, just like in this circuit, we could figure out what our initial voltage was. And so we have that we have that way of doing it. Of course, we can do it exponentially, but linear is nice because, with exponential, it's a real hurry at first, and then it's a really slow once you get down the curve. And a lot of mathematical models prefer a linear transfer characteristic to an exponential. So let's move on here. And one thing I wanted to mention is that I also posted a derivation of the formula that appears in page 365 of the Basic Stamp Syntax and Reference Manual. This is a formula for time, and we've seen a formula here. If you know the initial voltage, you know the time and the resistor and capacitor, well, we can tell you what the time is at some time t by kind of plugging in here and chugging through the calculation, and we'll get a voltage here. So let's do a little algebra here, and we'll swap around. We want to solve for t, so we know V of t is our ending voltage, and V initial, we know that's our initial voltage, and we know R and C. So divide both sides by V initial, you get a formula like this one. Then you, I don't know why that thing is there with a negative sign on it. Let's, I'll tell you what, let's just, let's just get rid of that. And I have no idea what the bloody hell I was doing there. But I now have this ratio, V final over V initial is equal to E minus TRC. Well, once we know that that the inverse function of exponentiation of this from the natural basis E is the natural logarithm ln. So if I take the ln of both sides, you get ln of this ratio, the E just goes away, and I have minus t over RC, and of course I can change any two signs of a fraction. The fraction has three signs, and numerator, denominator, and the entire fraction. I can change any two signs without changing the value. So I changed the minus sign out here, and I changed the minus sign in the denominator. So now I have t over minus RC. I multiplied both sides by minus RC, and I get this formula. The time to discharge from an initial voltage to V of t is minus RC times the natural log of the final voltage divided by the initial voltage. And in our case, if we were going from 4.5 to 1.4, and we were using 2,000 microfarads and a 10k ohm resistor, you can follow this calculation down here, and it gets 23.35 seconds. And we got 23 seconds that we counted out, and so at any rate, that's our that's our claim to fame there. We feel like we validated our mathematical model with our actual laboratory results, and I'd always be suspicious if you see that happening. This one here was done with a different circuit. It's the 10k ohm resistor, but a 0.1 microfarad capacitor. It works its way all the way down here to about 1.167. I like that, about 1.1676 milliseconds. We have no right to claim that kind of accuracy. That's not proper. So maybe call it 1.2 or 1.17, and whatever. But I just left the calculations from the calculator. All right, you have that document, and I'll update the one that's on the blackboard to get rid of those two steps in the middle that weren't right there. So let's go on to our next charge and discharge circuit. We will be taking a look at, going over here, we'll be taking a look at this built-in function from the this built-in function in the basic stamp, what's a microcontroller and basic stamp syntax and reference manual. Basic stamp has this thing called RC time, in which they actually do the work that we just did in one statement. So I'm going to change I'm going to get rid of these two capacitors here. And instead I'm going to install a 0.1 microfarad capacitor. And I don't think our meter will actually be a factor here, because this is going to happen very quickly. So I think we can maybe do away with that. Well, let's see how this works out. We're going to go back over here, and so we're going to start our program. We've got a variable called word. We're going to start our program. For 1 millisecond, we're going to charge, just in a thousandth of a second, we're going to charge the capacitor. If you look at our circuit, this guy is now 0.1. So I'll cross that out, and I'll put here we have 0.1 microfarads. Okay. So we have 0.1 microfarad here and 10K. So the time constant now is about 1 millisecond actually. 0.1, yeah, so this is 1 times 10 to the minus 4, and this is 10 to the positive 4. If we just calculate tau equals RC, we get 1 second. No, I'm sorry. This is 10 to the minus 7. This is 10 to the plus 4. We get, when we multiply them together, we get 10 to the minus 3, or 1 millisecond. So let's go back over to our program here. Now they're just going to charge this thing for 1 millisecond. It should take, now I think it should take like 5 milliseconds for this thing to charge up. But we're going to charge it up, and then RC time is going to take RC, which was declared as pin 7 again, and it will turn it to an input, and it'll, the 1 means it will be looking for it to discharge from a 1 to a 0, I believe. And if you're not sure of that, we can go to page 363 in the basic stamp and reference manual. And it's actually, I guess, here's page 363 coming up. So there's a pin number That's RC in our case, it'll be pin 7. And so there's a pin number, RC, pin, state, and variable. Our variable is result. Our pin is 7, and then this middle thing is a 1, which means that once the pin is not in that state, the command ends. So if you put it in a 1, it's looking to discharge until it's a 0. If you put in a 0, it's looking to charge until it's a 1. With a longer time being from 4.5 volts down to 1.4 volts, you kind of prefer to use the discharge curve, which would put a 1 in this state argument here. So we'll run this, and when we'll double check, I think we'll pause for 5 milliseconds to make sure we're completely charging that before we run it again. Well, what the heck? We'll do it now, just to make sure, because 5 milliseconds. What's 5 milliseconds between friends here? That's just the charge time. The measurement time comes after that. So I'm going to make that modification, and I'm going to run this this thing, and let's see. Let's go back. Oh, you can see a number running up here. It says 626, 627, and it's supposed to display that result, and then pause and go and do this again. So we just keep getting 625, 626, 627 each time through this loop. So that's what it's measuring. If I were to turn this resistor down maybe to the halfway point, something like that, instead of 627, I'm getting like 340. And I know that's probably too small for you to see, but it's 340. And if I turn it down to maybe a quarter of the way, be somewhere, let's see, somewhere about there maybe, I'm getting like, you'd think I'd get more like 160 or something, but I'm getting more like 140 here, so 146, something like that. So that's the RC time. It's timing the discharge for us, printing out a result, waiting 50 milliseconds, going back up and charging the capacitor for 5 milliseconds, and then taking as long as it takes to measure this. And the measurement time, I believe, is, if we look at this explanation here, the units for measurement time for the BS2 is 2 microseconds. So if we go back here, and I'm going to turn this back up to a full 10K, we're getting now we're getting like anything from 627 to 631. So 2 microseconds times that would mean that we're getting let's see, let's do it this way. We're getting about, I don't know, 1.2 milliseconds, 1.3 milliseconds. Let's see if let's see how we do against our calculations. So I'm going to slide this over. The reason I do this, by the way, is I happen to be running the document camera and the recording software on a Mac, and I run the PBasic editor under a Windows virtual machine on the Mac. So that's what all this fal-de-ral is here. Okay, so here's my basic stamp, here's my circuit, there's the thing that I've been adjusting, that little blue resistor there. And let's see if we can autofocus on this projector a little better, or on this meter. I'm not sorry, not a meter, calculator. That might be a little better. Okay, so what we have, let's take something like 630. Oh yeah, that's really visible. 630 times 2 times 10 to the minus 6, 2 microseconds. And it's very hard to see, but it says 1.26 milliseconds. All right, now let's calculate our delay time using that formula. So our delay time should be something like, and again, you know, maybe I can, let's see if I can do something like this. We're just going to do a calculation here, and then I'll move everything back. And we'll get this thing focused in here. Boy, it's kind of like it's too bright. And I'm sure there's a way to decrease the brightness. But hopefully you can see over here that it says 1.26 E minus 3. Well, that's 1.26 milliseconds. So if we use our formula, it's minus RC times the natural log of V final over V initial. Well, so let's do this. Let's do a negative 10 times 10 to the third. That's our 10K. I can barely see the negative sign. Times our capacitor is 0.1 times 10 to the negative 6 times the natural log of 1.4 divided by 4.5. You know, we usually start out at 4.5, and survey says, it says about 1.17 milliseconds. So we're in the ballpark. All right, it just shows you that I'm not BSing everything that I do here. And so you can see that we came, well, let's see what the world says here. Let's call it 1.17 milliseconds. So if I take 1.17 minus 1.26, and I divide it by 1.26, and we get that. So about 17% error. Yeah, I'd probably like to do a little better than that. You know, 10% sort of a golden number. If you're within 10%, you can BS just about anything. A little tip for your career there. But 17%, well, you know, this capacitor, actually, so we're running shorter. Now that I mentioned it, this capacitor was about 5% low when I tested its value. And the resistor wasn't that far off, so I can get 10% there, but why, you know, I'm sorry, I can get 5% low, but why I'm 17% low, I do not know. All right, so let's keep moving on here, and let's get on to our next situation, in which we're going to talk about PWM as an output. And in PWM, what we do is, there's actually a command in the basic stamp, PWM. You give it a pin number, you give it a duty cycle out of 0 to 255. So I guess you'd call it a duty cycle out of 256, and you give it a time in milliseconds. And let's go see what that means in the manual. And I will. I'm sorry. I'll cover up our formula. And I'm going to use a different board here. Okay, so let's go get our other program here. And let's also look up PWM in the command. Now and I'll add. Well, I've already put this one on Blackboard, but let me see if I can find it in the. There's PWM. So that's the 73 out of 76 places where this is mentioned. And let's go down in the index here. See how prepared I am. And we'll look at PWM is page 355. So here we're gonna talk about investigating the P-basic PWM command, pages 355 to 358. Let's see, let's go over here. And this is basic stamp syntax and reference manual. Okay, great. So what you'll see is I have a program here, and we'll go check out what the 10 milliseconds means. But what I'm going to do is on, now I have it set to use pin 15, so I will connect, disconnect pin 7 so it's not doing anything. And I'm going to connect up my other circuit board to pin 15. And what I'll do is I will bring back my meter. You'll see this in a second. I'll bring back my meter and show that that we're going to do something the other way around now. We have been showing how you can use time to measure we've been showing how you can use time to measure a voltage or resistance or capacitance, a way of kind of doing an analog to digital conversion. Now we're going to do a digital to analog conversion. We're going to put in numbers. So 255 out of 255, that should be 100% duty cycle, and that'll give us our full voltage out. 128 is about half of 256, so we should get about half our voltage out. 64 is a quarter, and 32 is an eighth. So we should see our voltage going down here in terms of these outputs, and we're converting these numbers right here, 255, 128, 64, and 32, to output voltages. And we'll run these things, so I guess maybe it's every 5 seconds, because there's a 10 millisecond thing here. We multiply it by, we're going to run this 500 times, so we get 5 seconds per, and you'll be able to see it on the meter. So one last thing though, let's go to page 355. And we're not quite there. Oh yeah, let's see, PW. Here we go, PWM. So you have a pin number, you have a duty cycle, and then cycles is constant expression 0 to 255 that specifies the duration of the PWM signal. So whatever, I don't know if it's milliseconds or not, but you will see, I also have an oscilloscope, and you will see the PWM signal indicate what it is we want to do. So units in cycles, so whatever these units mean, is 1 millisecond, so I guess that 10 does mean 10 milliseconds. And we're using a 1 microfarad capacitor and a 10 k ohm resistor. So now we have a time constant of 10 milliseconds. So, you know, we'll look, because maybe we'll change that that thing. And you can read in here how this works. But here's the circuit right here. It's 10 k ohm resistor with 1 microfarad capacitor to ground. That's a low-pass filter, so it's going to average out our pulses and give us something like a an output waveform that's been smoothed by the by this filter. So what I'm going to do is so let's go back to our program, and I'm going to run this program. And let's see, we'll get you a view. So let me run it from the start again, because it changed once already. Okay. So it goes up to almost 5 volts. And then it goes to half of that, and then it goes to a quarter of that, and then it goes to an eighth of that, and then it goes back to, you know, as close as it can get to the full thing. And I believe I can. Well, I'll swing a change over here on the oscilloscope. And we'll see if we can. Add an average value on here. Okay, so you've seen the pattern. I have the meter. Right. I have the meter. I guess we don't need this threshold marker anymore. Doesn't really help us. So I have the meter hooked up to the top of the resistor. That's the pin coming out of the microcontroller. And I guess maybe I can put the meter, I don't need to do that, put the meter right across the capacitor is probably the best thing. So now the meter's across the capacitor, looking at the averaged voltage. It's at 1/8, it should go to full now. And there we go. And I'm going to set this up so I can give you a shot of the meter here. Okay, so let's see if I can twist my camera here and show you what's going on in the screen. Okay. Well, it doesn't focus in very well on the text over there, does it? Let's see if we can do another autofocus here. Wow. I'm just going to have to read you what the screen says, I guess, or maybe I can do this. Let's focus in over here, the same distance, without something that's moving on the screen. Okay, great. Now let's move that over here. And what we have going on is, at first we have, this is channel 1, this is channel 2. So we'll actually wait for it to go around to the full thing. And you know, now we're down to maybe 1/8 or something, I think. Okay, here we are, and we've got about 4.6 volts as our full voltage. I'm measuring the voltage of channel 2, and now we're down to half of that. It was about now we're down to 1/4. It's like 1/1, and now we're down to 1/8. It's about 540 millivolts. Probably should be maybe 400 millivolts or something like that. Yeah, and here we went to full. Now we're at half. Half was about 2.3 volts. So because we're not making it all the way to 4.3 volts. I'm sorry, we're not making it all the way to 4.9 or 5 volts. Everything is running off 4.6. So now I'm 4.6 volts. So when I run half, it says 2.3 volts. That makes sense. When it says 1/4, it should be like 1.15, something like that. Yeah, 1.115, but it's close. And then, it says the duty cycle's 1/8, by the way. And now we go full, and the duty cycle has trouble because there's no edges, so it's 100%, 50%, 25%, if you can sort of make that out, and 12.5%. So we went from 1/4 to 1/8, and then we'll go back full. So we've shown there that we can drive out a waveform and low pass filter it, and we can affect the opposite. Before we were measuring some analog quantity and turning it into a number, so we had an analog to digital conversion of some sort. Now we're taking a number and converting it to what the oscilloscope said was kind of a smooth analog voltage, and so now we're affecting a digital to analog converter. And if you are interested in audio at all, Class D amplifiers do just this very thing. And there's a lot of very inexpensive chips now that do Class D amplification for use in small devices, portable devices, embedded devices, mobile devices, and they just control the duty cycle so that after you low pass filter the output, you get a varying audio voltage. So they're very quickly changing a duty cycle of a very quick pulse train, low pass filtering it, and getting an analog voltage that rises and falls just like a sound waveform would. Okay, so that's it for lecture 2. We're going to do one more lecture here, and that will involve measuring input pulse time with the pulse in command. And like I said, I'll post some homework. So this is week 3 into week 4, but we'll have some more content specifically for week 4. Take it easy, and we will see you soon.